Representing solutions to inequalities. So, before we can begin, we have to recall what it means to be a solution. A solution is a value of a variable that makes any statement true. Just keep that in mind. Normally, we're used to dealing with equations where there's one solution, but now we're dealing with inequalities, where you're going to end up with definitely more than one. Let's look at our first one. Here we would read this as x is greater than 2. How many solutions does it have? Well, let's start filling in some numbers greater than 2. 3, 4, 5, all the way up to 1 million and beyond. Not to mention also things like decimals, 2.7, 10.1. So we can't sit here and list all these values. It would take us forever and we never finish. So we could say that there are infinite solutions here. However, infinite in this case does not mean all, because there are some values that are not greater than 2. For example, we couldn't say that 1 is greater than 2. That wouldn't be a solution. 2 is also not greater than 2. That's not a solution. So it's infinite, but it's not all solutions. Let's take a look at this next one. The only difference here is that it's greater than or equal to 2. So how many solutions does this have? Well, it would have all the same solutions as the first one, 1 million and beyond, 2.7, 10.1. So it does also have infinite solutions. Again, not all solutions. But what does the second statement have that the first one doesn't? The second statement also includes 2 as a solution because of the equal to sign. So I would say this is infinite solutions plus 1 more, because 2 is a solution in the second statement, but not a solution in the first. So how do we represent all of these solutions? Because it's not reasonable to assume that we're going to have to write them all out. Well, there's a 4-step process, and we're going to look at that process with problem number 1. So problem number 1 reads x is greater than negative 3. So we need to somehow represent all numbers greater than negative 3. Well, first of all, we need to figure out where are these numbers starting. So what is the quote border point of our solution set? And that's going to be negative 3. This is called the border point. This is where your solutions start. So the border point is the only number in the statement. So 0, negative 1, negative 2, here's negative 3. So that means my solutions are either going to be to the right of negative 3 or to the left of negative 3. Next, we have to check 2 points. We're going to check 1 point to the right and 1 point to the left, because only one of those can actually be a solution. You can't have 2 of them be a solution. So I'm going to check negative 2 and negative 4. And you can already see that that's set up for you here. So to do this, we're just plugging it into the statement. Is negative 4 greater than negative 3? Or is negative 2 greater than negative 3? Remember, greater than means to the right of, or closer to positive infinity. So that means negative 2 is our solution here. This is the value that makes the inequality true. So I'm going to put a point on negative 2. And then thinking about it, if negative 2 is a solution and negative 4 was not, so I'm going to cross out negative 4, that means all the points on this side of the border are also solutions. Now, it doesn't make sense for me to just put infinitely many points. In fact, as you start to put infinitely many points, they're starting to form what's called a solution line, and that's step 3. We're going to create a solution line that contains the solution point from step 2. So here's how we do that. We start at the border point, and we're just going to draw a line all the way to the end of the number line with an arrow, because any number to the right of negative 3 will make this true. Now, the final step here is we need to determine if negative 3, the border point, is a solution. So that's going to lead us to the type of border point we use. If negative 3 is a solution, we want to put a closed point on it. Closed points are used to show solution. But if it's not equal to, we're going to put an open point to show that that's where our solution set starts, but it is not included. So let's zoom in here. Is negative 3 greater than negative 3? That is false, meaning negative 3 is not a solution and can't be included in our infinite solution set. So how do we do this in the graph? It's very tough, but what we're going to do is we're going to circle negative 3 to show that that's where our solutions start. But we want to make sure not to touch negative 3 because as soon as you put a closed point, that means that it's a solution, which in this case it's not. So now our graph is done. We have found all of the numbers that are greater than negative 3, all the infinite solutions. So let's try this same process on problem 2. Step 1, identify your border point. This is where my solutions start. And over here, I can see that negative 6 is right there. Step 2, we're going to check 2 points, one from either side. Only one of them will actually be a solution. So to do that, we're going to plug it into the statement. Is negative 7 less than or equal to negative 6? Or is negative 5 less than or equal to negative 6? Well, less than means to the left of, or more negative. And according to my graph, that's going to be negative 7. Meaning negative 5 is not the solution, but negative 7 is. So because it's a solution, it gets a point. And that means everything on this side also gets a point. All my solutions here will be to the left of negative 6. So step 3, I'm going to draw in my solution line. And it's going to extend all the way to negative infinity. Final step, though, we have to figure out, well, what about negative 6? Is that also a solution? Let's zoom in. Is negative 6 less than or equal to negative 6? This is true, meaning negative 6 is a solution. It should be included in our solution set. So that means when I zoom in here to negative 6, it deserves a closed point because closed points show solutions. And problem number 2 is done. This is the set of infinite solutions to the inequality x is less than or equal to negative 6. Last one. Problem number 3 seems easy, but one thing I notice is that my border point is now on the other side. So let's go through this one again. So my border point here is at positive 2, right there. The next step is going to check 2 points. I'm going to check a point to the left, which is 3, point to the left, which is 1. And only one of these can be true. Now careful, we're checking for x here. X is on the right. So either 2 is less than 1 or 2 is less than 3. Which one is 2 less than? Well, less than means to the left of, and 2 is to the left of 3, not to the left of 1. So 3 is my solution here. 1 is not. Which means everything to the right of 2 is a solution. Because if we think about it, these are the numbers that 2 is less than. You could have also rewritten this inequality as x is greater than 2. Because these are both saying the same thing. 2 is less than x, x is greater than 2. Either way, we have our solution line. Now we need to check the border point. Is 2 a solution? Well, let's zoom in here. If I were to plug in 2, is 2 less than 2? No, that is a false statement, which means 2 is not a solution. And since it's not a solution, I can circle 2 to show that that's where my solutions start, but I want to make sure that it's not included in my solution graph. And that's how we do number 3. So just to recap, the first step is to identify your border point, the only number in the statement. Check 2 points, one to the right and one to the left. One of those points will be a solution, that's where your solution line goes, and then check the type of border point. If it's equal to, it can be closed. Not equal to, it's open. Thanks for watching. See you next time.